let's start. So, so recall that for an elliptic curve E defined over Q, I have these associated invariants. Okay, so if I write delta for the minimal discriminant, okay, so this is the minimal discriminant. You have to take the minimal Weierstrass model for E and then compute the discriminant for that model.
You mentioned it only in the local context.
Okay.
So maybe you should say that there's a global.
Yeah, so there is a global Weierstrass model for which you can compute the discriminant, and then the minimal, what you call? The minimal one is the delta min, the discriminant of that minimal model. Okay, so I have an elliptic curve. You can write it in many ways, and then you can compute discriminant for each one of them. Okay, but there is one minimal one, this one. So minimal discriminant. Okay, and I write n for the conductor of E. Conductor of E, and the NP for the prime P is this number. So NP is defined to be n divided by product of all the primes. So these Q's are primes. Okay, Q divides n at most once, and P divides the order of delta. The order of Q in delta. So this is the power of Q that appears in delta, okay? And so theorem of Ribet was okay, that if I have prime number P which is bigger than or equal to 5, okay, such that E does not have any P isogenies. So this is very important. Does not have any P isogenies. And so NP, okay, so then there exists a new form F, of this level here, this level NP, level NP, such that E is congruent to F mod P. It means that you take the modularity theorem of Wiles says that there is a modular form which is associated to E. You take the Fourier coefficients, of this. They're congruent to each other modulo a prime that lies above P. Okay, so this is the theorem. And I have some just two remarks which I want to make, which is that so this theorem requires the modularity of E, okay? So it means that, okay, so this notation means that the cusp form is associated to E, so this is congruent to F mod P, by which I mean that the Fourier coefficients of this are, so this is almost everywhere, okay? So this is almost everywhere. Okay, so this is important. So for all the primes, at all the primes away from this, away from NP, away from N, the Fourier coefficients here are congruent to the Fourier coefficients here modulo P. P square, we can have a version of Ribet's level lowering. But you need some more conditions other than just having irreducible, mod P irreducible Galois representation. Okay? P square there is. So the remark is that Ribet's theorem requires E over Q modular. Okay. And yesterday I also said that if I have F, a new form F, and if it's all its Fourier coefficients are rational numbers, then F is said to be a rational new form. But how on earth are you going to check? It has got infinitely many Fourier coefficients. How are you going to check? So there is a bound. Okay, I think it's the so the number field. Yeah. Yeah, assuming. Yeah. So this number field K, okay, which is nothing but Q adjoined with all the Fourier coefficients here, C2, C3, so on. Okay, so this is determined by finite number of Fourier coefficients. Okay, so I think if you go till so if you go like if you start so my modular form is going to have a weight and a level, right? So you start computing like you compute C2, you compute C3, and if you go till C like K times n squared, then you are safe. Okay, so this K is equal to, so this is more precise. Okay, it's more precisely. K is equal to Q C2 C, okay, K. So you need fewer than this actually. Square. Yeah, so you can actually check, you can fit this into the machine and it will compute it, and then you can determine from here. So if this is Q, then you can declare that it's a rational new form. Okay, so what else? Yeah. So now, so let's try to solve, so my aim is to solve this equation. So x to the p plus L times L to the power r, y to the p plus z to the p equals 0, okay? So if x, y, and z they're all 0, then I have a trivial solution where x, so let's condition x, y, z is not equal to 0 and p is bigger than or equal to 5, right? So again,
Why do you need this assumption to greater than?
yeah, so because I want to apply this Ribet's level lowering theorem.
Why does he need that? Does he use something about?
Yeah, so so the thing is, you need for Ribet's level lowering condition, you need a stronger form of irreducibility, which is absolute irreducibility, and to go from irreducibility to absolute irreducibility, if p is greater than or equal to 5, then you are safe. I mean, if you have an explicit elliptic curve, then somehow you can work around. But yeah, so if you have specific elliptic curves, then you can. I see. So maybe it's not needed. Yeah. So maybe it's not needed. So again, what I'm going to do is, so remember the steps that we did. So I'm given this equation, and I have to prove that it doesn't have any non-trivial solutions. Okay, so I'm going to cook up an elliptic curve out of this. Okay, and then compute the discriminant, and then compute this NP, and then use Ribet's level lowering condition, and then show that there are no modular forms, and then somehow get a contradiction, right? Okay, so let's do that. So let x, y, z. Okay, so this be co-prime, pairwise co-prime, pairwise co-prime. Okay. And let's assume that 0 is less than r, less than p. Okay. If it is more than p, then you can absorb that power in y. Okay. So I can safely assume that my r is less than p. Clear? Oh, okay. So L is let's say n. Then, so again, note that all of them cannot be odd, or so one of them has to be even. Again, so as all x, ly, and z cannot be odd. Okay, so this is clear. So one of them is even, and the remaining is odd. Okay, so in the remaining two of them is odd. Okay, so I'm going to say, okay, so one of them, yeah, so this is congruent to -1 mod 4, okay? So, yeah.
Why can't they all be odd?
Yeah, so because if for example, this is odd, then z is forced to be even. Yeah. So, so some of you were asking me, like when we did yesterday, x to the p plus y to the p is congruent to 0 mod 4, and I said that, so one of them will be 1 mod 4, the other one will be -1 mod 4. Where do you actually use it? So when you compute the conductor of the elliptic curve, you have to use the States algorithm, right? So there you will see where it is used. Okay. Sorry? If L is?
L is even.
Yeah. Yeah. If L is even, then Ly is even, then X and Z have to be odd. Okay. So one of them among this is X, Ly, Z is congruent to -1 mod 4. So I'm just going to write. So let A denote that number. Okay. So let A be such that A is congruent to -1 mod 4. So A is one of them, one of those. X, Ly, and Z, which is congruent to -1 mod 4. Okay, so among, so let me write here, X, Ly, and Z. Maybe I write here X to the P, L to the R, Y to the P, and then Z to the P. This is okay, and let's say that the even one is denoted by B, and 2 divides B. Okay, so now I look at the Frey curve. Okay, so this is E, which is given by y squared equals x times x minus a times x plus b. You could have taken here x, say, minus the remaining one. Okay, so I have chosen a to be one of this, b to be one of this, and the remaining one you could have taken. Okay, so maybe I'll prove to you later on that that curve will turn out to be a twist of this elliptic curve or isomorphic. Then, okay, so let's, yeah, mod 4. Okay. So then let's compute the minimal discriminant. So I have to use Tate's algorithm, for which I have to start out by assuming that this is an elliptic curve. Okay. B is the one which is, one of them is even, right? So I'm calling that to be B among one of this. Yeah. So the delta main is 2 to the minus 8. So please go back home and then check the conductor or all these things. Yeah, it's well implemented in magma. So 2p, and then n, the conductor turns out to be the radical. Okay, so radical is nothing but the product of the primes that appear in here. So product of the primes that appear in this number, just the product, no powers. So, and NP compute turns out to be 2L here. Okay, so I've computed. So now I make one more assumption, which is, okay, so assumption. Which is that L is odd. Okay, L is odd prime. Yeah. Then again, for curves like this, right? You know all the two torsion points. They all lie on the real line, right? And because y will be 0 there. And so note that the two torsion points, Q, so will be given by this, right, along with the point at infinity. So you have exactly 4 points there. It's important. Therefore, by Mazur's theorem, if n is square free, if n is, so as n is square free, so which means that my curve E, so this is a semi-stable elliptic curve. Okay. Sorry? N is the conductor of this elliptic curve. This one. Also, this is product of all primes Q such that Q divides L, X, Y, Z. Okay? The primes that appear in this product. But you have to take only one at a time, only one prime. Okay. Q divides exactly.
No, if there is some power, you ignore that.
Yeah. So, that's right. So, so as in n is square free, so this guarantees that E does not have P isogenous, right? Therefore, by Ribet's level lowering theorem, there exists a new form f of level np, and np as we computed is 2L. 2L such that E is congruent to F mod P, like this. Yeah. Okay, so now let's see where do we have new forms. Okay, so now I'm going to write a going to make an observation. Where do I have new forms at what level? Okay, and so this f is of weight 2. Okay, this f, this is of weight 2. New form f of level np and then weight 2. Okay, so but now you note that there are no new forms okay, so at level I'm going to find out for what else there are no new forms. Okay, at level 1, 2, 3, 4, 5, 6. So this means weight 2. Okay, new forms of weight 2, 6, 7, 8, 9, 10, 12, 13, 16, 18, 22, 25, and 60. Okay? So there are no new forms at this. So therefore, I don't have solutions. So let's give a name to this equation. Let's say this is 1. Or maybe say this is 1. Okay, so therefore 1 does not have solutions. So therefore 1 does not have solutions for what values of L? Okay, 6. Yeah, so the level is 2 times L, right? And L is prime, so 6. Isn't it? L equal to 6. The next one will be 10 here, right? Because it's 2 times 5, and 5 is prime. Sorry? Oh, yeah. Sorry. 3, 5, and 3, 5, 12, or 3, 5, 13, 16, 22, right? So 22 is 11 here. Am I right? Yeah. So at this, when L is equal to 3, 5, 11, there are no solutions, you're guaranteed. But now, suppose what happens at the other levels? Okay? So let's see, let's examine it a bit more. What happens if the same technique is going to work or some other thing? Yeah, but if I have, what happens if you have some other number? I don't know. Huh? Yeah. Yeah, so yeah, I really don't know why do we need L to be prime number here, but the problem is in computing this radical. I think if you don't have a prime number, then you have a problem. This and computing the radical, the conductor, I think. The NP doesn't turn out to be 2 times L. Yeah, so the NP doesn't turn out to be 2 times L. Can be more complicated. The NP doesn't turn out to be 2L. Yeah. You can have some more other factors. Yeah. Okay, so Yeah, so this is done when L is equal to this one. So now let's look at, so suppose what happens when, say, L equals 19. So L equals 19. So this I sum in. Then, of course, my NP here will be 2 times 19. Then you have new forms. Okay? Then, so the following, okay, I'm going to write down the new forms. So it's of dimension 2 are the new forms of weight 2 and level 38. Okay, so the first one is say F1 equals Q minus Q squared plus Q cubed plus Q to the 4. So remember that Q is e to the power 2 pi I z. Okay, minus Q to the 6 minus Q to the 7 plus and so on. And then F2, this equals Q plus Q squared minus Q cubed plus Q to the power 4 minus 4 times Q to the power 5 minus Q to the power 6. Like this. Sorry? Yeah, so P is a prime number which is bigger than or equal to 5. For any prime, P bigger than. Yeah? So now let's look at the possibility of having a congruence with F1 and the modular form that arises from the elliptic curve, okay, and then see what we can do about it. Okay, so now, suppose, so let's see if I can have a congruence with E and F1, okay? So so congruence with F1. Okay, I'm going to examine the possibility. So now, so remember that, so recall that we have AL of E is a number which is less than or equal to 2 times the square root of L, right? This is the Hasse bound. So therefore, what can I say about A3E, right? So this is an integer, by the way, okay? So this is either equal to 0, 1, 2, or 3, right? So now, so let's make an assumption again here. So suppose 3, I want to examine if I can have a congruence with this coefficient, the coefficient of Q to the power 3 and A3. That's why I'm interested in 3, this 3, okay? So suppose that P does not divide, 3 does not divide P times, okay, 38 times N here, okay? So N is the conductor of the elliptic curve, so radical of L times XYZ, okay? So suppose that 3 does not divide that, okay? So it's a prime of good reduction. And I have P bigger than or equal to 5, okay? So these are not issues, this is not an issue, but 3 dividing, this may be an issue, so I impose this condition. So then we have, then I want to look at A3E minus C3, which is 1 here, okay? So C3, okay? So I know only the absolute value of A3E. So let's look at, so I want to find this out, so let's rather look at this, A3E squared minus, so this is equal to minus 1 or 0 or 3 or 8. Okay, so C3 is equal to 1, so if you put in. So therefore, if P is bigger than or equal to 5, then P is not going to divide this one, and this one, right? But P may divide, it may as well be 0. Then that's a typical case. So therefore, if P is bigger than or equal to 5, so therefore, so as P is bigger than or equal to 5, so it does not divide minus 1, 3, 8, right? So you cannot have a congruence. So if your A3E is one of them, 0, 2, or 3, you cannot have a congruence. So your A3E is supposed to be such that the square has to be 1 because you have 0 here. Okay? Yeah. So unless here A3E, there are better ways of doing this, by the way. So it's equal to 1. So this is not a. So now, as I've assumed that 3 does not divide this, so 3 is a prime of good reduction. So I know that. So recall that my A3E is equal to 3 plus 1 minus the number of points on the reduced elliptic curve mod 3, right? So this is equal to 4 minus the number of points on F3 here, right? So by this I mean the points on the reduced elliptic curve, okay? So even if I have used E, so this is only a notation. So this is equal to E. Okay? So therefore, what can I say about the number of points? So this is equal to 4 minus A3E. Okay? So now I use one result from Anupam's talk, okay, and Sujata's talk, which is the following. I'm sure you will know a proof of this also. Okay, remember this curve and N and NP, so we have to use it. So then, so what I'm going to say is the following, that so what do we know? So we know, or we saw that I have, so suppose okay, so that EQ can be embedded inside EQP, right? So I have to choose an embedding from Q to QP, right? So a point here you can write as homogeneous coordinate x, y, and z, and then each one of them can be embedded inside this by having an embedding like this. So then we saw that, and I have so since E is a prime of good reduction, so we have here, I don't know, was it ENS? So ENS will be the whole of this, the non-singular part. It will still be an elliptic curve, right? So E, so F here, and then E QP here, and then you have something called the formal group. Okay, this is 0 here. So you have the formal group here. You have the elliptic curve here, the local model. Okay, and then you have here, and then this is a surjection here. Yeah. So now you can. Anupam was talking about the formal group. This E hat, and the moment that if you choose a number m, okay, maybe, so suppose if m is prime to p, right? So this is, must be given in Silverman also. Then E, okay, E hat to E hat, the multiplication by M map is an isomorphism. This is an isomorphism. Okay, so what it means is that, so what does this, so now, so note that if M is co-prime to P, then you look at the m torsion points on the elliptic curve here. Okay? The m torsion points on the elliptic curve here, you can realize them as points inside this. Okay? This will not come from the formal group. Okay? Because multiplication by M map is an isomorphism, so the torsion points are going to be inside this, the M torsion points. This is a very important observation. Okay, it's simple, but we are going to make certain estimates using this. So therefore, so let me write here itself. So therefore, E Q M can be embedded inside E F D. Yeah? So in fact, this is one of the good ways of finding torsion points on the elliptic curve, right? So if you can choose whatever prime that you want. If this is 0, then you know that it does not have any torsion points which are co-prime to this. Okay, so this is well done. I mean, given in Silverman's book, I think. So what does this mean? So if I know that, okay, yeah. So now, so another thing is this, and then so further, I know that E Q, the torsion part of the elliptic curve. So this is finite, right? So, and suppose, and so combining all these things together, so therefore, if I have a number T that divides this, okay, E, Q, tors, then T also divides the number of points on E, FL, okay, provided, so if L is co-prime to T, right? So this is true. So this is important. Any questions? 3. Yeah, then, so therefore, I know that in our case, I know that I can take M to be equal to 2, right? 2, and then, so therefore 4 has to divide EF, the number of points inside F3, right? So therefore 4 divides the number of points inside E. Right? So since the number of points as E Q 2 equals to 4 here. Okay? So therefore, so this means that 4 divides 4 minus A3E. So this implies that 4 divides A3E, right? So what does this mean? So my A3E, the mod, cannot be equal to 1, right? So the mod of mod of A3E is not equal to 1, right? So at least I cannot expect to have. We did this under the assumption that 3 is a prime of good reduction. So I cannot expect to have 3 to be a prime of good reduction and then still expect solutions. Okay? So therefore, this is a contradiction, right? So this is contradiction. So try to figure out the case when 3 divides n at most once, okay? Then you have to use the congruence, okay? So suppose 3 divides n, then you know that you'll use the congruence here. L plus 1 is congruent to plus minus CL. But then you'll have a problem. Okay? Right? So I'll just shortly write down here. So maybe here. Okay? So here. So you will have come up with a situation where minus plus minus C3. Okay? So this is equal to 4 minus plus minus 1. Right? So which means that it can be 5 and that's divisible by 5. So you will not have a contradiction, right? So you have to do something else, okay? But we'll do this, okay? But remember this, okay? F2. Huh? Is it okay? All right. So what are we doing here exactly? Let's try to abstract. What are we doing here? What are we doing here? Okay. So I'm trying to use an actual. I know that my E arises from a modular form, and I'm trying to see whether P divides this number, right? P divides this number. Yeah, so arising from that, congruence arising from that. Okay, so I'm going to give a name to this number, and the possibilities for A3 are what? See, look at this. These are numbers, integers that lie between -2 root L and 2 times root L. Okay, so I'm going to collect all those integers. Okay, so I'm just writing down what we are doing here. T divide E, Q here. So this is the finite group, right? And either P equals to L or P divides A, LE minus CL, okay? But then I know that the CL can be a number which lies in a bigger extension of Q, right? So I take the norm here. Because this is P, I take the norm of K over Q, right? This is the case when L does not divide N, and or again here, P divides L plus 1 whole squared minus CL squared here. And again, I take the norm, so the norm of K over Q. Okay, so this is if L divides N. Okay, now, so remember this bound here. Okay, we are not done with this, with the solution of the problem, okay? So I'm just taking what we are doing here. So we'll come back to this. So suppose L does not divide N, then I know that A, L, E, so this is less than or equal to 2 times root L, okay? And if T divides and T divides E, the number of points inside FL. Okay, so which means that T divides L plus 1 minus AL or E. Okay, so I collect. So therefore ALE, so now is in the set, belongs to this set here. So S here, so which is defined by all the integers that lie between plus minus minus 2 root L to 2 root L, to such that mod of A is less than or equal to 2 root L, or and A is congruent to 1, mod t. So you see this mod t appearing here? T was my 4 here, the choice of t is equal to 4 here. Okay, so I'm just trying to make everything formal, okay, and then yeah, it's better because we want to make the process to, becomes better. It's clear. Steps. So now, so we define this number. Okay, it's this number. What I'm going to write down is this number, 4 minus A3E. It's just that there can be many other terms. Like, for example, I also want to include the case when, 3 is a prime of multiplicative reduction. Okay, so but it's essentially it's this. So define B L prime of F. This is this number. What is that? The norm of K over Q. So the norm of K over Q, L plus 1 whole squared minus CL squared, and then the product of A inside all. So SL. So did I have an SL here? So maybe I write an L here so that I know this L is here. And then the norm of K over Q, A minus CL. Okay? So instead of looking at the ALEs, what I have done is I'm looking at all the possible integers that lie between minus 2 root L and then 2 root L, and I'm making this product. Okay, so this removes the dependency on the ALEs. Okay? So somehow I can run this, no matter what elliptic curve do I have, I can run this independently. And I define one more number. Okay, so you put here B L F. So, sorry? Depends upon T, yeah. So this is L times BL prime F if my F is not rational, and somehow, and you don't need this L if you have a rational modular form, so you have here BLF if F is rational. Okay, so the entire proof is just follows from the fact what we have done, that the torsion points on the elliptic curve, okay, so they can be embedded inside the reduced points on the elliptic curve if you have a prime of good reduction. So you can work this out, but I just give you the idea. So the proof is enough to. Easy, observe that. EFL, so you just have to make sure that this L is away from the number of, the torsion points here. So sense of this, and then proposition follows. So okay, so what does this give me? Okay, this proposition, what does it give me? It's allowed to do. So suppose I pick a prime L, I compute BL. Okay, I have not written down the conclusion, okay? So let me write here. So if E is congruent to P mod F, then E divides BLF. Okay, so this is the conclusion now. So what does this tell me? This tells me that you compute BLF. You have the freedom of taking this L. Many L's are there, okay? You have the choice. Now, you can take, say, suppose I compute there, for example, in my case, B3F. Now, I can compute B5F. And if I know that B3 and B5 are co-prime, then I will know that my P is fixed, right? There won't be any primes. And then that's how we can get a contradiction, right? So let's try to implement this. So let's go back to L equals 19. Okay, we'll examine one more case, L equal to 31, but later. So suppose, yeah. So now, let's compute here S3. So here L is equal to 3. So this consists of all integers where this is less than or equal to 2 root 3, and your A is congruent to 4 mod D here. Okay, so the only choice you have here is A equals 0. Okay, let's find this out. Now, let's compute. So this F is rational, okay? My F1 is going to be rational, okay? So F1 is a rational new form. Okay, all the Fourier coefficients are going to be inside Q. Okay, and so therefore, BL is nothing but BL prime, right? So let's compute BL prime. So B3 prime F1, so this is 4 squared minus 1 times minus 1, so this is minus 15 here. So therefore, yeah, so therefore, okay, and now next consider S5. S5 is all those A such that 2 root 5, and then A should be congruent to 6, but mod T. Okay, and this turns out to be minus 2 and plus 2, plus minus 2. Therefore, B5 prime F1 so is equal to, so here 6 squared minus 0, right? L plus 1 whole squared minus 0, and then negative 2, negative 0, and then 2 minus 0 here. So you have here 36 times 4, so that's, and then a negative sign here, so that's minus 144, right? So therefore, B5 F1 is equal to minus 144, right? So as I said, now P has to divide 15 and P has to divide this. So can you tell me one prime which divides both of them? P bigger than or equal to 5 which divides both of them don't exist, right? So therefore, you arrive at a contradiction. So GCD of B3 F1 and then B5 F1 equals 1. So equals, no, it's not, it's 3, right? I mean, how much it is? It's 3. So this is a contradiction. P is bigger than or equal to 5. Okay, so I have now eliminated F1. I had two possible choices, one F1 and F2. I have eliminated F1. Okay, so so I just write down for F2. So suppose I have E congruent to P and congruent to F2 mod P, then just compute this compute this. I will leave it. I know the values, but I'm not writing down here. Compute this. Okay. So anyway, so you just check. This turns out to be 15. Just to save time. So F2 is 240 and D7. F2 is 11, 55, and then B11. F2 is 3360, right? So okay, then you will see that there is a problem if E is bigger than or equal to 5, okay, and then you get a contradiction. So the point is that these numbers, BLs, are very useful, and it allows us, right, to get a lower bound. So the contradiction is obtained by this number 3. So if my P were equal to 3, then you could have probably something else happens. So this allows us to get a lower bound on the powers P. Okay, so that's why this technique is also known as bound on bounding exponents. Okay. Okay. So, but okay. So maybe I can complete the proof. It's very nice. You need some other facts on Galois representations. Okay. So you see that this ends in 5, this ends in 0, this ends in 5, this ends in 0, right? So it's of course divisible by 5, and then so E equals to 5 divides all of them. But the GCD turns out to be 5, by the way. Okay, so you still have to eliminate, you still have to work extra for P equals to 5. Okay, so so now I ask, is BLF2, okay, always divisible by 5, always divisible by 5. What happens if it's always divisible by 5? Okay, so careful, I mean, this is very interesting. So what do we know? So we know that, so let's write down, so I know that, so I have this new form, F2 of wet 2, okay, level 38, right? So now you go to Cremonna's tables, you open up and then look, what are the elliptic curves of level 38 which corresponds to this F, okay? Then you find that this corresponds to the elliptic curve okay, so let's give a name to this F, which is 38B1. Okay, so I'm assuming this. Okay, I'm going to assume that if it is always divisible by 5, what happens? Okay, so now, so let's assume that, so let 5 divide BL F2 for all L. Yeah? You need extra inputs from Galois representations. So I'm just going to write that down. And you immediately see why this is not possible. Okay? So, so the number of, so this can be calculated. So note that number FQ is equal to 5. Okay, this you can calculate. Okay, and then this implies that 5 divides L plus 1 minus CL. CL is the Fourier coefficient for here. Okay, and it will also be congruent to the Fourier coefficient for this ALF. Okay, so therefore 5 divides BL F2, and which is nothing but L plus 1 minus CL, and then L plus 1 plus CL, and then A minus CL. Okay, A belongs to O. And then can I take some more minutes because we are almost done? Okay, so so if L does not divide n times n prime, okay, then I know that ALE is congruent to CL mod 5. Okay, so now my P is 5 here, mod 5, and right, and so and L plus the number of points, and I know that 5 divides what, L plus 1 minus CL also, so therefore 5 divides L plus 1 minus ALE. If L divides N. Okay, so now you see that sorry? If L divides N prime, so L does not divide N, right? So I can have N because what was the level? N is radical of Lx, y, z, right? So let's write N prime for that. It's no problem. N prime is the N prime is NP, so which is 2 times L, right? So and I know that. So basically, the point is that 5 divides L plus 1 minus CL for all L. So what can this mean? So it means that, so this is, right? So, yeah, so this implies that L plus 1, 5 divides L plus 1 minus ALE because these two are congruent mod 5, right? So this means that you look at this Galois representation, yeah, with 1 and chi, okay? And then that will be congruent, the trace of that Galois representation is nothing but ALE, right? So what does that mean? That means that the mod P reduction, mod 5 reduction of the Galois representation attached to E is reducible. But we have just shown that if P is bigger than or equal to 5, then it's irreducible, okay? Using Mazur's theorem. So this is a very nice, so I end with this, but just let me write down one line. Okay, so therefore the Galois GQ representation, say chi 5001, okay, is the cyclotomic character, okay, is congruent to rho E, okay, bar here. Rho E bar will be the semi-simplification of the reduction mod P of this rho E. Okay, so this follows by what you call the Chebotarev density theorem. Density theorem, right? So this implies that rho E bar is reducible, okay? Which means that E has a 5 isogeny. But we have shown that Mazur's theorem does not have a contradiction, right? By Mazur's theorem, right? therefore we don't have, cannot expect to have any solutions. Okay. Therefore, one does not have any solutions. So any questions? Okay. NP is a factor of n. Yeah, so this is sufficient. I'm just writing because I was writing Ribet's level lowering. There I always use n prime.
So for 2 also this is true. No? Initially you started with x to the power p plus L y to the power p plus.
Yeah, see if you choose L equal to
2, that is
2. That's true. So for L equal to 2, we need separate treatment actually.
Yeah, true.
Yeah. Okay, so tomorrow I don't have one, but the next one involves a little bit more on Galois representations, and we'll be looking at x to the power n plus y to the power n equals z squared. There we will see how having rational points on elliptic curves with complex multiplication, the points of infinite order, which Anupam has said how it comes and how it helps in proving that there are no solutions. Yeah.
Your title for the lecture was BSD and
Yes.
Chandrakant.
Yeah.
But there's not so much BSD.
Yeah. So tomorrow when I do x to the power n plus y to the power n equal to z square, we will see how having non-trivial, points of infinite order helps in helps us in showing that there are no solutions.
And there you need the full force of BSD or only
No.
BSD?
The weak is enough. Weak is enough.
Pretty soon this involves some like computer also, right?
Yeah, because you cannot
They can all this.
Yeah, you cannot list the
So if you
new
can
forms.
comment a little about those computational aspects.
Yeah, so we are going to have one session on Saturday maybe. Yeah.